So this is pretty much all I'm going to show you from section 3.3, and hopefully you'll read everything from it on your own. So when you read through proofs, make sure that you're not just accepting everything on authority, but you're also becoming convinced. So read like a skeptical person, and don't let proofs convince you if they're not convincing. Go ahead and ask about anything that doesn't convince you. That's definitely a good thing if you're not convinced by things so easily. So one thing of note that I haven't covered in lecture is this theorem 35, iterated relative complement. That's an interesting one, and I haven't covered it. So this is worth reading, I think. And one thing I like about this one is that I show you a couple of different approaches. One that relies on a lot of heavy symbolic work and direct use of logical rules, and another approach that is more wordy. So you can see both of them and what the different approaches look like. Another thing I want to get into is this comment about absolute complement. So we have our relative complement, right, where we've defined A with B deleted, but it is kind of tempting to define absolute complement. So maybe instead of taking A and then deleting B, just sort of deleting B and then not saying where we're deleting it from. So something like some notations that I've seen used for something like this is B superscript C for complement, or B wiggle, or B bar, something like that. And what you might want to define it to be is the set of things, rather than the set of things that are in A and not in B, you might define it to be the set of things that are just not in B. This turns out to be problematic. And the problem is related to the bug mentioned earlier, the way in which axiom 5 is broken. But it takes a lot more work to see why it's a problem. So remember we mentioned earlier that this axiom is a little bit too powerful. There are certain propositions that if you try to apply it to that proposition, then you end up in a paradox. You end up proving a contradiction and breaking all of math. So since we are doing naive set theory, our approach is not to fix the problem, but to basically ignore it and say there are certain bad things that we should not put here for propositions because they will lead to paradox. Interestingly, one of the bad things you can put is a proposition like this. So we don't do that. And we don't use absolute complement. We don't use that idea, at least not until we fix the problem, which we're not doing in naive set theory. And this is why what we have is relative complement. But typically typically when you're taking sets and deleting something from them, typically when you're taking a complement, you don't want to consider everything that's not in a particular set. Usually your complement is taking place in a certain background world. So, for example, if you're doing real analysis or something, then all the sets you're interested in are subsets of the real line. So when you take a complement of a set, you don't want this kind of absolute complement. No, you want to subtract a set from the real line, so delete it from the real line. So you do a relative complement. So in real analysis, you would study the real line, denoted by R, something like that. And if you have a certain subset of the real line, like A, then you would take its complement like this. Take R and then delete A. You wouldn't just... And, you might use, as a shorthand for this, you might just write A complement or A wiggle or something. But you wouldn't define something like the set of all things that are not in A. That would be a ridiculous thing to work with. Okay, one last thing I want to do is look at proving this exercise 51.2. And I'm not looking at this because it's particularly interesting. It's actually very much not interesting at all. But I want to look at it just to give you some feel for how to make arguments, how to argue that a set is empty. Because sometimes it can feel pretty awkward to prove that a set is empty. Let me show you why I think this is awkward. So first of all, look at this and convince yourself intuitively that this is true. It looks pretty true, right? If you take a set and you delete from it everything that's in it, then you should end up with the empty set, right? You should end up with a set with nothing in it. So the reason I say this is awkward is, how are you going to prove this equality? Probably axiom 8 or theorem 10, right? So let's say I use theorem 10. So proof. So proof, you'll do something like this, right? Consider any z in the left-hand side, a without a, and then now your goal becomes to prove that z is in the empty set. And then if you succeed in that, then consider any z in the empty set, and then your goal becomes to prove that z is in a without a. Okay, so this is really weird. How are you going to prove that z is in the empty set under the assumption that z is in a without a? The empty set is empty. Nothing is in the empty set. How in the world can you prove this? Well, you're in a situation where you can prove it because your assumption is equally ridiculous. To assume that z is in a without a is to assume that z is in a and not in a, right? That's a straight up contradiction. Z in a and z not in a. So you'll immediately get to this kind of thing, which is a literal contradiction. Then you can conclude anything you want. In particular, you can conclude this, just because from a contradiction you can conclude anything you want. Similarly here, consider any z in the empty set. That's already ridiculous. Now you can conclude anything you want, including this if you want to. So this will lead to a working proof of this equality, but it's super awkward. It feels really weird to do it this way, I think. Whereas the idea that this is equal to this did not feel like such an awkward idea. It felt very intuitive, right? Take a set, delete everything from the set, delete everything in the set away from the set, remove it. You end up with an empty set. That just feels like a natural statement. So why the logically convoluted proof? Okay. So what I suggest to avoid the awkwardness, unless you like the awkwardness, then that's fine. But what I would suggest is use the following. Theorem 14. Theorem 14 tells us it tells us that only the empty set is empty. But it is a way of proving not equalities in general, like axiom 8 is a way of proving equalities. Theorem 10 is a way of proving equalities. Theorem 14 is specifically a way of proving that things are equal to the empty set. So it tells us, if you want to prove that something is equal to the empty set, then try to prove this. Try to prove that that something has no elements. So if a set has no elements, then it equals the empty set. So if we use that theorem, then with that approach, the task becomes prove that a without a has no elements. You see? And that I think is much more natural. That's the reason we think of it as being the empty set, is because it has no elements. So let's look at how you would write up such an approach. So the goal, in order to prove that a without a, in place of a here, equals the empty set, I need to prove that for all x, so this is a quantified statement, but it's just written kind of in English, I need to prove that for all x, x is not in a without a. So my goal, prove that for all x, x is not in a without a. So that's the goal. So to prove that, to prove a universal, I do universal generalization. Consider any x. And now my goal becomes, now that I've considered any x, my goal has become prove that x is not in a without a. Okay, well, a good way to prove that something is not true, if I think it's ridiculous for that thing to be true, is to do a proof by contradiction. So suppose, for the sake of contradiction, that x is in a without a. Now let's see how that's ridiculous. Then x is in a and x is not in a. right? According to the definition of relative complement. And there we go. That's a contradiction. Therefore, this is a contradiction. So let's see. Maybe I can organize my paragraphs a little better by creating some space here. No, actually, I think I'd like this to go together. No. Let's do like this. Yeah, so start a universal generalization, prove by contradiction that x is not an A without A. So now we've done the universal generalization, we've proven this. Then by theorem 14, I think it was. Yep. By theorem 14, since we've proven that this is an empty set, we have proven that it is the empty set by theorem 14. So this is a nice way of proving that sets are empty. Just prove that for them to have an element is contradictory.